Hi everyone, I wanted to make a video to address the last few objectives in 8.1. So far the objectives we've covered have really been very mathematical, calculating concentration and calculating concentration from a dilution or from making a solution from a solid. But the last two bullets here talk about describing the process of dissolving for soluble ionic compounds versus soluble molecular compounds, and it's important that we understand what dissolving really means and describing the difference between electrolyte and non-electrolyte solutions. So maybe in elementary school, dissolving and disappearing kind of sound like the same thing. When you put some salt or sugar in water and stir, wow, it's gone. And then maybe a little bit older, you start to realize that when you dissolve something, it doesn't disappear, but I imagine that a lot of students in younger grade levels, disappearing and disintegrating and dissolving are pretty easy to get confused. So hopefully we develop an idea that dissolving is really a matter of the solute breaking into smaller and smaller particles until those particles are so small that they're no longer visible. And that's accurate. But we want to develop an even more sophisticated model of what dissolving is. It's true that the solute particles break apart, but we want to understand exactly how that works. So let's talk about dissolving and what an electrolytic solution is. These notes are also online, and they're the same ones we'd go through in class together. So this video hopefully will clarify some of those points. We know what an aqueous solution is. An aqueous solution is simply a solution that has water as a solvent. And here you guys see two beakers. Can you tell which one is the sugar and which one is the salt water? They're both just a solute dissolved in water. And it should be obvious the one on the left-hand side of the screen is the sugar water, right? Well, of course, I just took two stock images that are identical, but even though they're the same image, if they really were one being sugar water and one being salt water, we'd see an interesting effect when we try to pass an electric current through that solution. If both of these were dissolved in distilled water, the sugar water would show absolutely no conductivity. And that's because it has no electrolytes or ions in solution. It's a non-electrolytic solution. Whereas the salt water, being consisted of ions in solution, would conduct electricity. There's an important difference between how sugar dissolves in water and how salt dissolves in water, because sugar is a molecular compound and salt is an ionic compound. Sugar is a molecular compound, and therefore it breaks apart into molecules, whereas salt is an ionic compound, and so it breaks apart into ions. Molecules have no charge, and so on the left, there's no charged particles in solution, and therefore current can't flow. And on the right, since there's ions in solution, which are charged particles, then current can flow. So I'd like to try and show a model of what this looks like at the molecular level. And I found a couple of good images here that I think illustrate it well, although they're in different styles. On the left, you see a crystal of sugar, and on the right, modeled is a crystal of salt. And if you had a sugar grain and a salt grain on the table, you probably wouldn't be able to tell them apart without tasting them. But they're fundamentally different in terms of how they're structured. The crystal sugar, the grain of sugar crystal, is actually a whole bunch of sugar molecules that are held together by weak intermolecular forces. And the water can disrupt those weak intermolecular forces and cause the sugar to dissociate into molecules of sugar. The salt, however, is a network structure of cations and anions. And the water can disrupt those ionic bonds by forming ion dipole interactions and causing the salt to dissolve. But the mechanism for dissolving is very different in each case. The result, of course, is that we have molecules in solution here, which are neutral and no conductivity. We call that a non-electrolytic solution. And on the right, we have ions in solution, which do conduct electricity or allow for the flow of electricity, and so we call that an electrolytic solution. So I'd like to take a look at the model that I had on the right. And I'm going to try to demonstrate that using a model kit that I used before. Remember that the ionic compound there is consisted of green and purple anions and cations respectively, and I've even got some cute little water molecules that just look like the ones in the picture. Let me show you what I mean. I'm going to go to remind you a little bit about intermolecular forces. Here are some water molecules, and these models are kind of neat in that they have magnets in them, and you can see they're demonstrating what we learned before is a special type of intermolecular force called a hydrogen bond, right? That attraction between one molecule and another is a hydrogen bond. Now I'm also going to introduce, and I only have one of these, unfortunately. Having a whole set of them was a bit too expensive, but this is the chloride anion and the sodium cation representing salt. So what happens when salt gets put in water? Well, the positive end of the water molecule, where there is a partial positive charge, is going to be attracted to the anion in the salt molecules, and if that occurs several times, then you'll see we start to surround the anion with water. And of course, this is a sodium cation. The negative partial charge on water will be attracted to that positive cation charge, and sooner or later, if we start to surround the entire salt unit cell with water molecules, the salt will actually become dissociated. And you can see here the cation is surrounded by water molecules. Each one is being attracted to the cation by its negative side, and that's called a hydration cell. And here the anion is also surrounded by water molecules, and essentially what we're looking at here is this ion dipole interaction is overcoming that ionic bond, and the ionic bond eventually becomes disrupted, and we have sodium ions free in solution, and we have chloride ions free in solution. These are dissociated ions, and this is a fundamental process that's important to understand in aqueous solution chemistry. So that showed how an ionic compound dissolves in water. Let's consider how a molecular compound will be a little bit different. Here's a whole bunch of water molecules, again, attracted to each other by those intermolecular forces we call hydrogen bonds. And instead of introducing a salt, I'm going to introduce a molecular substance. The molecular substance is not sugar, like in our previous example. It's methanol, and methanol is CH3OH, and you can see that there's one methanol molecule and there's another methanol molecule. These are actually going to be attracted to each other by hydrogen bonds as well, another weak intermolecular force. So, how does this molecular substance dissolve in water differently than the ionic substance did? We're not actually going to be breaking chemical bonds. We're just going to be disrupting intermolecular forces, which is very different than the ionic substance where we actually broke chemical bonds. Here, we're simply disrupting intermolecular forces. Water forms intermolecular forces with the solute particles, and the solute particles end up getting farther and farther away. So you can think about having molecular substances dissolve in water as really a matter of dispersion rather than dissociation. So hopefully that clarifies what these pictures are supposed to show. Let's talk about what I mean by that word dissociation. This is an important term that I want to introduce, which refers to an ionic compound splitting or separating into ions in water. Notice for a molecular substance, there is no formation of ions, but for an ionic substance, if it dissolves in water, that means it dissociates into ions. So if we write NaCl(aq), in other words, salt in aqueous solution, what it really means is that the salt has dissociated into sodium ions and chloride ions. Similarly, if we're talking about aqueous lead-2 nitrate, which is what that formula and subscript indicate, that really means that the lead-2 ions and the nitrate ions have dissociated. And hopefully it's clear that we will actually get 2 nitrate ions for every 1 formula unit of lead-2 nitrate that we dissolve. So when we say lead-2 nitrate is in aqueous solution, what we really mean is that lead ions and nitrate ions are separate in aqueous solution. Notice in this case, we're actually indicating that the silver chloride is solid, which means it is not dissociated into ions. And this is a critically important point. Silver chloride, it turns out, is insoluble and will not dissolve in water to any significant extent. All right, we just have one other point that I want to introduce here, and we've already kind of laid the groundwork for it. You see on the far left, we've talked about the case where you have a non-electrolytic solution. In other words, a solution in which all the solute particles are molecular. There's no ions, and so there's no conductivity. On the middle, you have a strong electrolytic solution or a strong electrolyte. All of the solute particles are ions, and so charge is free to flow. And the one case that we haven't considered is what is called a weak electrolyte. And in a weak electrolyte solution, the solute is only partially composed of ions. Most of the solute particles do not dissociate or ionize into charged particles. Most of them stay as molecular substances, and you will not get a great amount of conductivity in that solution. So let's talk about each of those a little bit more carefully. The first case, non-electrolytic solutions, are cases where none of the solute particles are ions. 100% of the solute exists as a molecular substance. Sugar dissolved in water, ethanol dissolved in water, methanol, like the examples we looked at before. No current flows in that case, like you can see in the picture. Strong electrolytes are solutions where all of the solute particles form ions. If it's a soluble ionic compound, it's going to form a strong electrolytic solution. Strong acids are also strong electrolytes. Every mole of solute becomes ions. The last case is a weak electrolyte. In a weak electrolyte solution, very few of the solute particles actually form ions. In other words, most of them stay as a molecular species, but a few of them will dissociate or ionize, and so you'll see some conductivity in this solution. And this is what a weak acid is classified as. Weak acids, we'll learn, are a substance which only partially ionize in solution. So again, here's that summary between a non-electrolytic solution, a strong electrolytic solution, and a weak electrolytic solution. That wraps up our discussion of electrolytes and dissolving. Let me know if you have questions, and that's the end of Unit 8.1.